The universe is vast, cold, and, well, it seems endless, doesn't it? But humans, we've spent millennia trying to put a border on it, some kind of definitive fence around existence. That drive to find the edge, the Canton, Render, Grenzen, as our sources put it, that's what we're really diving into today.
It is the ultimate paradox, isn't it? You have this sheer, almost terrifying vastness of the cosmos, a place that seems to just go on forever. And then there's our deeply ingrained human need for structure, for orientation. We kind of need to know where the perimeter is just to understand where we are.
Exactly. We've seen programmed to define limits. And what our source material really highlights is that for a very long time, this idea of a limitless universe wasn't just, scientifically baffling. It was theologically and politically dangerous. Challenging the idea of a bounded cosmos could literally cost you your life.
Which is why this deep dive feels so, well, critical. Our mission here is to trace the path of that curiosity. We're looking at the sources that document how we went from just guessing, really, to methodical measurement, how we invented the tools, everything from simple sticks and shadows, all the way up to interstellar probes and space telescopes to try and measure the unmeasurable.
Yeah, we want to understand these walls we've encountered, both the physical ones and the theoretical ones. Can we actually glimpse the edge of existence? And if we can, what does that boundary tell us about the ultimate size, the shape of everything? Okay, so let's unpack this journey. Maybe we start with the greatest boundary pusher we've ever built. Voyager. We can't fly to the edge of our solar system ourselves, definitely not the universe, so we sent these messengers. Voyager's traveling for over 4 decades now. It's that lonely scout out there.
The name itself, Voyager, means traveler, and its sheer longevity, its current status, being the furthest thing humans have ever sent out, it's just a testament to brilliant engineering. Launched back in 1977, the 2 probes, Voyager 1 and 2, their initial goal was actually relatively constrained, believe it or not. They were meant to do a grand tour of the 4 outer gas giants, Jupiter, Saturn, Uranus, and Neptune.
But even that initial goal, the scale is just immense. I mean, these planets are spread out over billions of kilometers. How do they possibly get the speed and the range needed to complete that kind of tour without just running out of fuel?
This is where the technical planning meets a kind of cosmic luck. To cover those staggering distances, the probes needed huge boosts in acceleration. The key was using gravitational assists like celestial slingshots, where the spacecraft basically steals a bit of energy from a moving planet. But this needed a very specific, incredibly rare alignment of the planets.
A planetary chain, I think our sources called it.
Precisely. Calculations showed that Jupiter, Saturn, Uranus, and Neptune would line up in just the right way, allowing a single probe to use each one after the other, as a gravitational launch pad. That specific lineup, it only happens once every 176 years. The window opened up in the late 1970s. If they'd missed 1977, humanity would have had to wait until, well, the 22nd century for another shot.
Wow. That planning is just... It's the height of astronomical foresight, isn't it? It's not just luck. It's like 200 years of physics planning squeezed into one launch window.
Absolutely. So the engineers launched these identical probes, but on slightly different paths. Voyager 2 was the main pathfinder for the full grand tour. And just 2 years later, the images coming back from Jupiter completely changed how we saw that planet. Before Voyager, models suggested it was, fairly static, just a gas ball. But the probes revealed this volatile, dynamic place racked by storms, even from 600 million kilometers away.
And the data just kept pouring in. What surprised us most about Saturn when Voyager 1 got there?
Oh, the rings. Definitely the rings. Before Voyager, our telescope suggested maybe 1 or 2 main ring structures. Voyager 1 and 2 showed thousands of complex ringlets, weaving, braiding, structures made entirely of rock and ice chunks. The solar system was suddenly infinitely more complex than we'd pictured.
Then came that really long haul out to the outermost giants.
Yeah, Voyager 2 was the real endurance champion there. 5 years after launch, it reached Uranus, over 3 billion kilometers out, crazy distances. And then 12 years after launch, it finally reached Neptune. The images of Neptune showing these winds and storms, the most powerful we'd seen anywhere in the solar system, that marked the successful kind of official end of the original planetary mission. It was humanity's advance guard, really defining the edge of our immediate planetary neighborhood.
But the journey didn't stop there, did it? After the cameras were turned off, because, well, there wasn't much left to take pictures of in the darkness of deep space, the mission entered its second phase, an even more profound one, maybe, defining the true boundary of our sun's influence.
Exactly. This is where the instruments themselves became the explorers. We needed to know how far the solar wind traveled. You see, the sun is constantly blasting out about 1 million tons of charged plasma particles every single second. This stream flows outward and creates this huge protective magnetic bubble around the solar system. We call it the heliosphere.
And that bubble is really critical, isn't it? It sort of shields us from the really high-energy galactic cosmic rays coming in from deep space.
Precisely. So Voyager's particle detectors and its magnetometer, they were tasked with finding where the pressure from that solar wind finally gives way to the pressure of the stuff between the stars, the interstellar medium. And the boundary isn't neat. It's not like a solid wall. It's defined by two key physical events.
Okay, could you break those down? What exactly was Voyager looking for?
Right, so first is the termination shock. This is where the solar wind suddenly slows right down from supersonic speeds to subsonic speeds. It creates a kind of shock wave. Voyager 1 crossed this point way back in 2004, about 14 billion kilometers out. But the solar wind was still there, just moving slower. The second, the really definitive boundary, is the heliopause. That's the physical and magnetic edge where the outward pressure of the solar wind completely balances the inward pressure of the interstellar medium. It's the true edge of the bubble.
And when did we actually know for sure that Voyager 1 had crossed that ultimate threshold?
Well, by late 2012, the data, which by then was taking something like 15 hours just to travel back to Earth, showed 3 really clear changes. First, the number of charged particles coming from the sun, the solar wind particles, just dropped off a cliff. Radically, almost to zero within about half a day. Second, the direction of the magnetic field suddenly flipped, showing it wasn't connected to the sun's field anymore. And third, there was this dramatic sudden jump in the levels of high-energy galactic cosmic rays.
So those cosmic rays, the ones that the heliosphere had been filtering out, they suddenly flooded the probe's detectors. That instantaneous shift meant Voyager 1 had definitely left the solar bubble.
It was undeniable and empirical confirmation. Almost 18 billion kilometers out, it had entered true interstellar space. Voyager 2 followed it across that same boundary in late 2018. It is the furthest human-made object, just this silent scout out there, defining the boundary of our home star system.
Yet even this incredible journey faces an ultimate limit, one we can't really negotiate with, as you mentioned, that inevitable last beep.
That's the immovable wall we just can't get past. The probes are powered by these things called radioisotope thermoelectric generators, RTGs. They use the heat from decaying plutonium to make electricity. But that power source is finite. The power output drops by about 4 watts every year. Eventually, there just won't be enough juice left to run the science instruments. Or, crucially, the heaters needed to keep the hydrazine fuel lines from freezing solid.
Right. And once the hydrazine freezes, the probe can't aim its antenna back towards Earth to send us any data.
Exactly. We figure sometime in the mid-2020s, maybe a bit later, we'll get that last meaningful data packet. And after that, Voyager just becomes this silent, cold artifact, carrying its golden record with sounds and images of Earth, traveling essentially forever through the galaxy. We'll never know what it encounters next. It's a profound, definitive boundary, one defined simply by our human technology eventually failing against the sheer scale of cosmic distance.
That technological boundary you just described, it feels mirrored by earlier, much more dangerous boundary, defined purely by belief. But before thinkers could even challenge the cosmos, they first had to figure out how to measure their own world, right? Let's jump back, way back, 2,000 years or so, to a time when these intellectual breakthroughs had to fight against purely mythological explanations for everything.
Yeah, that shift from mythology to actual measurement is arguably the single most important step in the history of science. We look to the 3rd century BCE, to Alexandria, which was really their intellectual hub of the ancient world. And the key figure here was Eratosthenes of Cyrene. He was the chief librarian there, a real polymath, who insisted that the world had to be understood through objective observation, through calculation.
Which was a pretty radical stance back then. Our sources mention how people still relied on stories about gods and monsters, like Scylla and Charybdis explaining dangerous currents, just to make sense of things they couldn't predict.
Eratosthenes basically rejected that whole framework. He understood that to map the world, you first needed to know its shape and its size. Now, the idea that the Earth was a sphere wasn't totally new. Scholars were debating it. But Eratosthenes really nailed it down with rational, observable proof.
What was his most compelling proof for the Earth being curved?
It was actually beautifully simple. Observing ships. He pointed out that if you watch a ship sail away from shore, its hull disappears below the horizon before the sails or the mast do. If the Earth were flat, the whole ship would just shrink evenly until it vanished. Only a curved surface could explain why the bottom part disappears first.
Okay, so he established the curvature.
Yeah.
But how do you then measure the size of that curve? How do you get the globe's circumference without being able to physically walk all the way around it?
This is Eratosthenes' real moment of genius. It's this amazing blend of observation, geography, and simple geometry. He used the difference in shadow lengths between two cities that he knew lay almost directly north-south of each other on roughly the same line of longitude or meridian, Alexandria and Syene, which is modern Aswan.
And his observation depended on one very specific moment in time, right?
Yes, exactly. The summer solstice, right at noon. In Syene, which is located very close to the Tropic of Cancer, Eratosthenes knew from reports that the sun was directly overhead at that moment. Apparently, its reflection could be seen shining straight down a deep well, and vertical objects cast no shadow at all. It was the solar zenith.
But meanwhile, back in Alexandria, at that exact same time, objects did cast clear, distinct shadows.
That difference was everything. Eratosthenes knew the sun was so far away that its rays arrived essentially parallel to each other by the time they reached Earth. If the Earth were flat, the shadows in both cities would have been identical. The fact that the angle of the sun was different could only be because the Earth's surface was curved between those 2 points.
So he measured the angle of the shadow cast by, say, an obelisk in Alexandria.
He did. He determined that the shadow indicated the sun was off the vertical by about 7.2 degrees. And here's the critical leap. He realized that this angle, the difference measured at the surface of the Earth, was equal to the angle formed by lines drawn from those two cities down to the center of the Earth.
7.2 degrees.
Right. And 7.2 degrees fits into a full circle, 360 degrees, exactly 50 times. So all he needed now was the actual distance between Syene and Alexandria. He relied on reports from professional surveyors called bemetists, people trained to measure distance very accurately by counting their steps. They estimated the distance at about 5,000 stadia.
Hold on, 5,000 stadia. How does that translate to modern units? I know the exact length of a stadium back then is a bit debated.
That's a really good point, and it highlights how good his method was, even with uncertain units. His calculation was based on the ratio. So 50 times that distance gives a total circumference of 250,000 stadia. Now, depending on whether he used the slightly shorter Egyptian stadium or the longer Attic stadium, that converts to somewhere between, say, 39,600 and 46,000 kilometers.
Wow. Considering the modern accepted value for the Earth's circumference is about 40,075 kilometers, even his lower estimate was astonishingly close. That's a measurement nailed down 2,200 years ago using just geometry and observation. Incredible.
Yeah. It really established the kind of intellectual rigor needed for all future cosmic exploration. He used rational measurement to define a local boundary, the size of our world. But that very rationality, that way of thinking, fueled the next wave of thinkers who used it to challenge the biggest boundary of all, the supposed fixed limits of the cosmos itself. And those challengers, well, they faced extreme danger for doing so.
Which brings us right into the 16th century and the story of Giordano Bruno.
Indeed. For over 1,500 years after the Greeks, the dominant model of the cosmos, which was heavily backed by the church, was considered unchanging, absolute. It was the Aristotelian Ptolemaic model. A fixed Earth at the center, God's special creation, surrounded by these nested, solid, crystalline spheres. These spheres carried the moon, the sun, the planets, and the outermost sphere, the fixed sphere of the stars, that was the absolute edge. Beyond that lay only the divine, the realm of God.
And Bruno, who was actually a Dominican priest himself, started arguing for something completely different, completely contradictory.
He argued, based on a mix of theology and emerging scientific ideas, that the universe had to be boundless, infinite. His reasoning was partly theological. An all-powerful God wouldn't create a small, cramped cosmos. He proposed that our sun was just one star among countless others, scattered through infinite space. And each of those stars could potentially have its own planets, maybe even harboring life.
Why was that idea of infinity so incredibly threatening to the established powers, to the church?
Well, think about it. If the universe was infinite, it immediately knocked Earth off its pedestal as the unique, divinely ordained center of everything. And if there were infinite worlds, then the biblical story of creation, original sin, the unique sacrifice of Christ, it all suddenly became potentially just one local event, statistically insignificant, maybe even incomplete. The boundary wasn't just physical, it was the very foundation of the church's cosmic map and its moral authority.
But even as Bruno was promoting these philosophical ideas, actual astronomical observations were starting to provide some scientific backup for his, well, heretical claims.
They were. Observations, especially by astronomers like Thomas Digges in England, began to suggest those crystalline spheres weren't real. First, you had things like novae, new stars suddenly appearing in the heavens. If the sphere of stars was perfect, unchanging, crystalline, how could new things just pop into existence there?
Right, it shattered that whole idea of the perfect static heavens.
And second, comets. They were observed not just moving through our atmosphere, but way out, far beyond the moon, seemingly traveling right through the spaces where those supposedly solid, impermeable spheres should have been. The physical boundary, the spheres themselves, were starting to look pretty flimsy under actual observation.
And of course, if the Earth itself moved around the sun, as Copernicus had suggested, and it was gaining traction, then the stars didn't need a sphere to carry them around anymore. They could just be stationary out there in infinite space.
The spheres became unnecessary, as Diggs pointed out. Bruno took this growing conceptual openness and fused it with his really stubborn theological belief. The universe must be infinite. He was absolutely convinced this was an eternal, unchangeable truth, and he traveled all over Europe arguing for this vision.
A vision that unfortunately led directly to his tragic end.
Yes. He was arrested by the Roman Inquisition in Venice in 1591 and extradited to Rome. The charges against him heavily featured his assertion of infinite worlds. After 8 long years of imprisonment, interrogation, and almost certainly severe torture, he was given a final chance to recant his views. He refused to abandon his belief in an infinite universe. So in February 1600, Giordano Bruno was burned at the stake in the Campo de Fiori in Rome. He paid the ultimate price for daring to challenge the most profound physical and philosophical boundary of his era.
It's sobering. Yet, fast forward 4 centuries, and his core ideas, our sun being just one star among billions, the existence of countless exoplanets, that's now standard astronomical knowledge. The only problem back in 1600 was they had the idea, but absolutely no way to measure those vast distances he imagined.
Exactly. Bruno's universe was this magnificent philosophical concept, but it was completely out of focus, you might say. To actually prove the sheer scale of his infinite vision, science needed a tool. They desperately needed a cosmic yardstick, something to calculate the distances to the stars. And it took over 300 years after Bruno's death for that crucial key to finally emerge.
Incredibly, it came not from some celebrated male professor at a famous university, but from this group of women working in a very specific, often overlooked, and quite restrictive environment.
That's the fascinating story of Henrietta Leavitt, working at the Harvard College Observatory in the early 20th century. Back then, astronomy was very much a male-dominated field. Leavitt was one of the so-called human computers, women hired, often for low pay, to do the incredibly meticulous, painstaking work of classifying and cataloging thousands upon thousands of stars captured on glass photographic plates.
Right, they were essentially compilers of data, not interpreters. Their job was to sort by brightness, measure positions, keep records. They were strictly forbidden from actually analyzing the deeper meaning of the patterns they were finding.
Leavitt herself was known for being incredibly meticulous, really focused qualities that perhaps sadly might have been enhanced by her progressive deafness, which limited distractions. Her specific assignment was to classify variable stars, stars whose brightness changed over time in a regular pattern.
Okay, so what specific type of variable stars was she focusing on, and what was the breakthrough discovery she made around 1912?
She concentrated her work on a type called Cepheid variables. These are typically large, very luminous stars that physically pulsate, growing larger and smaller, hotter and cooler, which causes their brightness to vary over very regular periods, often days or weeks. By meticulously studying Cepheids photographed in the small and large Magellanic Clouds, 2 nearby dwarf galaxies, Leavitt made a crucial realization. Because all the stars within one of those clouds are essentially clustered together at the same vast distance from Earth, distance itself wasn't a factor confusing her observations of their brightness.
That's the key insight, isn't it? If they're all roughly the same distance away, then any difference in how bright they appear to us must reflect a real difference in how bright they actually are, their intrinsic luminosity.
Exactly. And by comparing hundreds of these Cepheids in the Magellanic Clouds, she discovered this direct, unmistakable pattern. The longer the period it took for a Cepheid to pulse from bright to dim and back again, the greater that star's actual intrinsic brightness.
Wow, that one simple relationship, discovered by a human computer, patiently analyzing spots on glass plates, completely changed cosmology. How did this turn these stars into a universal measuring tool?
It transformed them into what astronomers call standard candles, or maybe think of them as standard light bulbs. If you know how bright a light bulb truly is, its wattage, you can figure out how far away it is just by seeing how dim it appears. Once astronomers could determine the true absolute brightness of a distant Cepheids simply by measuring the timing of its pulsations, its period, they could then apply the basic physics of how light fades with distance. Light intensity drops off predictably following the inverse square law.
So by comparing the Cepheids' known absolute brightness figured out from its period to its apparent brightness as seen from Earth, you could calculate its precise distance even if it was incredibly far away.
It finally provided the cosmic yardstick that science had lacked since Bruno's time, and even before. Before Leavitt, astronomers could really only measure distances reliably within our own Milky Way galaxy using parallax, a method that just doesn't work for truly distant objects. Suddenly, they had a way to measure distances stretching into the millions, even billions of light years.
It really is a tragedy that Henrietta Leavitt passed away from cancer in 1921, probably completely unaware of the monumental impact her discovery was about to have.
It is. She was actually nominated for a Nobel Prize shortly after her death, but the rules prevent posthumous awards. Her work's true triumph came just 2 years later, in 1923. That's when the astronomer Edwin Hubble used her period luminosity relationship Leavitt's law to measure the distance to several faint patches of light, then called spiral nebulae.
And that measurement proved that the Andromeda Nebula, for instance, wasn't just a cloud of gas inside our own Milky Way, but was in fact an entirely separate gigantic galaxy millions of light years away from us.
Exactly. The known boundary of the universe didn't just get pushed back, it exploded outwards. The Milky Way wasn't the entire universe. It was just one island galaxy in a vast cosmic ocean containing billions of others. Leavitt's meticulous work validated Bruno's centuries-old philosophical vision and gave us the scale we needed to enter the modern era of deep space observation and understanding the true immensity out there.
So with the boundaries of the universe now being measured in billions of light years, thanks to Leavitt's discovery, the next logical step was to try and actually see that vastness more clearly. This brings us, of course, to probably the most iconic tool in modern astronomy, the Hubble Space Telescope.
Yeah, even after Leavitt and Hubble had conceptually blown the doors off our view of the universe's scale, telescopes stuck here on the ground still face that fundamental, unavoidable barrier, Earth's atmosphere. It twinkles the stars, sure, but it also distorts, blurs, and absorbs huge amounts of light, especially in crucial wavelengths like infrared and ultraviolet. It severely limits how sharply we can resolve very distant, faint objects.
So to get truly unparalleled clarity, the solution was conceptually simple, if technically mind-boggling.
Yeah.
Just get the telescope above the atmosphere entirely.
That was precisely the goal. Launched in 1990 into orbit over 500 kilometers up, the Hubble Space Telescope was designed to deliver these incredibly sharp, pristine images of the cosmos. It was meant to be our clearest window yet, peering right to the edge of space and time.
But the launch was famously followed by, well, a disaster. The first images came back blurry, fuzzy, threatening the entire multi-billion-dollar project. What exactly went wrong, technically?
The flaw was tiny but had devastating consequences. Spherical aberration. The main mirror, which was polished to an extraordinary degree of smoothness, was ground to the wrong shape, but only slightly. The curve was off by just 2/millionths of a meter, that's less than the width of a human hair. But it meant that light reflecting from the outer edges of the mirror focused at a slightly different point than light reflecting from the center.
Basically, it gave the most advanced telescope ever built a bad case of nearsightedness.
That's a good way to put it. The fix required one of the most complex and daring space repair missions ever attempted. The 1993 servicing mission by space shuttle astronauts. They installed a set of corrective optics, basically a device called COSTAR, Corrective Optics Space Telescope Axial Replacement, which functioned like a precisely designed pair of glasses for the telescope, compensating for the mirror's flaw.
And once that fix was in place, Hubble started delivering the incredible results it was built for, immediately helping us define the boundary of our observable universe. And here's the key concept, I think, that we really need to emphasize for you listening. Looking deep into space is looking back in time.
That concept is absolutely fundamental to grasping the ultimate boundary we inevitably run into. The speed of light, while incredibly fast, is finite. It's the cosmic speed limit. So when we look at our own sun, we're seeing it as it was about 8 minutes ago, because that's how long its light took to reach us. When we look at Sirius, the brightest star in the night sky, we see light that left it 8 years ago. The Andromeda Galaxy, the nearest major galaxy to us, we see it as it was 2.5 million years ago. So the deeper Hubble looked into space, the further back into the universe's history it was actually seeing.
And to really push this to the limit, astronomers carried out the famous deep field observations. They pointed Hubble's most sensitive cameras at tiny, seemingly blank patches of sky for incredibly long periods.
Yes. The patch of sky targeted in the original Hubble Deep Field was unbelievably small, like looking at a grain of sand held out at arm's length. It looked empty to other telescopes. But by staring at that spot for over 100 hours, accumulating photons one by one, Hubble captured the extremely faint light from thousands of galaxies that had never been seen before, stretching way back in cosmic time.
And the most profound results came later, when they used even better cameras and pushed the exposure times even longer, right?
Exactly. The subsequent Hubble Ultra Deep Field, and then the Extreme Deep Field, XDF, involved staring at tiny patches for hundreds of hours. These images captured light from the oldest and most distant galaxies ever observed at the time. We were seeing light from the very early universe, maybe only a few 100 million years after the Big Bang, when the first stars and galaxies were just starting to ignite. And this brings us face to face with the true, final, immovable boundary.
Which isn't defined by distance in space, but by the passage of time itself.
Precisely. The universe, according to our best cosmological models, is not infinitely old. It began with the Big Bang approximately 13.8 billion years ago. Therefore, the absolute furthest we can possibly see, no matter how powerful our telescopes become, is the distance light has been able to travel in those 13.8 billion years. We simply cannot see light that would have needed, say, 15 or 20 billion years to reach us because that light hasn't arrived yet. Or going even further back, it originated from a time before the universe itself existed or before it became transparent enough for light to travel freely.
So we've effectively hit the cosmic horizons, like a wall in time, a boundary defined by the age of the universe.
It is the ultimate observational limit. Hubble pushed right up against it, and now the James Webb Space Telescope is peering even closer to that dawn of time. But no matter what technological marvels we build in the future, we can never receive information light or anything else from before that time-based boundary. Everything beyond that light travel distance, anything that happened before the universe was about 380,000 years old and became transparent, remains forever hidden from our direct view. It's like an infinitely high wall determined solely by the cosmic clock.
It's an incredible thought, isn't it, that every observer anywhere in the cosmos is similarly bound by their own cosmic horizon, standing effectively at the center of their own 13.8 billion light-year bubble of observability. Okay, so if the observable universe, this 13.8 billion light-year bubble we can see, has this definitive time-based boundary, it naturally leads to the grandest, maybe unanswerable question. What about the shape and the size of the entire universe? The whole cosmos, including everything beyond our horizon.
Right, this is where we really get into the deep end. Physics starts to blend with pure mathematical speculation, but it's speculation grounded in some pretty amazing measurements we can make. Astronomers basically use geometric models to try and understand the possibilities for the universe as a whole entity.
What are the main possibilities? What kind of overall shapes could the universe have?
Well, you can think about our three-dimensional universe having one of three fundamental geometries, and which one it is depends on its overall density of matter and energy. The first possibility is a closed universe. This would have positive curvature mathematically similar to the surface of a giant four-dimensional sphere. In a closed universe, space itself would be finite, although unbounded. If you could somehow travel in a straight line far enough, you'd eventually loop back around and return to your starting point.
Okay, finite but unbounded, like walking on the surface of the Earth. What's the second option?
The second is an open universe. This would have negative curvature, often visualized as being shaped like a saddle or a Pringle chip, mathematically speaking. An open universe would be truly infinite in extent and would expand forever. You could travel in any direction indefinitely without ever finding an edge or returning to your starting position.
And the third possibility, the one that our current measurements seem to point towards.
That's the flat universe. This geometry has zero curvature, like a perfectly flat, infinite sheet of paper extended into three dimensions. This specific geometry happens if the universe's total average density of matter and energy is exactly equal to a specific value known as the critical density.
Okay, critical density. Why is that particular density value the magic number that determines flatness?
Think of it as the tipping point in the cosmic tug-of-war between gravity trying to pull everything back together and the expansion pushing everything apart. If the universe's actual average density, including all matter, dark energy, everything, is greater than this critical density, then gravity eventually wins, the expansion stops and reverses, and the universe is closed and finite. If the density is less than the critical density, then the expansion overcomes gravity forever, and the universe is open and infinite. Our most precise measurements to date, especially from studying the cosmic microwave background radiation, the afterglow of the Big Bang, show that the universe's measured density is incredibly, remarkably close to that critical density.
Meaning the geometry of the part of the universe we can see, our observable bubble, appears to be flat. And that tells us something about its ultimate fate, doesn't it?
It suggests that the universe will likely expand forever. If it's perfectly flat, the expansion rate will gradually slow down over time, asymptotically approaching zero, but never quite stopping or reversing. It would only theoretically stop after an infinite amount of time. But here's the kicker, the paradox that really stretches our intuition. If the universe started from a finite point in space and time, the Big Bang singularity, how can the entire resulting cosmos be perfectly flat? Flatness usually implies infinite extent.
Right. If the whole thing is truly finite, even if it's gigantic, we should be able to detect some tiny amount of curvature from our vantage point within it. But our best measurements show it as flat.
Which leads to this mind-bending conclusion. If the universe is actually finite and curved, like a closed sphere, then it must be absurdly large. The radius of that overall curvature must be so enormous that the segment we can observe, our 93 billion light-year diameter observable universe, is just too small a patch to detect the overall curve. Imagine being an ant on the surface of a perfectly smooth beach ball the size of the Earth. The tiny patch you can see around you would look completely flat, even though you're on a curved surface.
So we can't measure the curve, but we have reason to suspect the universe might ultimately be finite, just vastly larger than what we see. What kind of scale are we talking about for this potentially enormous closed universe?
To appear as flat as it does within our cosmic horizon, the minimum possible radius of the entire, potentially closed universe has to be staggeringly huge. Our sources estimate this minimum radius could be something like 10 meters. That's a 1 followed by 86 zeros.
That number is just. It's beyond human comprehension. To try and put that in perspective, astronomers estimate there are maybe 10 fundamental particles, protons, neutrons, electrons in the entire observable universe. So the scale difference between the number of particles we can see and the minimum radius of the theoretical whole universe, if it's closed, is still a factor of a million. The sheer magnitude is almost insulting to the imagination.
That scale effectively becomes a boundary in itself. If the universe is finite and closed, that mind-boggling scale means that for all practical human purposes, its ultimate boundary is irrelevant to us. We'd never reach it, never perceive it. Yet the very measurement of flatness remains the strongest clue we have that perhaps the universe truly is infinite, or at least expanding towards infinity. It's the final, profound, open question in our long quest to find the cosmos's edge.
What a journey. We've tracked humanity's relentless effort to define boundaries. From Eratosthenes patiently measuring the curve of our local planet, to Giordano Bruno bravely and fatally imagining an infinite theological cosmos, then Voyager physically crossing the boundary of our solar system into interstellar space, and finally Hubble and Webb pushing our sight right up against that ultimate 13.8 billion year time limit imposed by the universe's own history.
And throughout it all, that fundamental human drive to explore, to push against limits, even when we're blocked by physical constraints like the end of Voyager's power, or fundamental temporal limits like the speed of light, that drive just seems unquenchable. It's the engine of all our knowledge. And maybe the most humbling realization is that we are all right now listening to this, standing at the exact center of our own individual observable universe, bounded by that same cosmic horizon. We know the wall is there, in time, and yet conceptually we're already trying to think past it.
So what does this all mean for you, thinking about this? If the edge of what we can see is set by the age of the cosmos and the unwavering speed of light, and if our best measurements tell us the universe looks flat but might still be finite, just incomprehensibly vast, what's the most profound takeaway from that sheer, almost ungraspable magnitude?
Perhaps it's this. If the universe is a closed loop, the very reason we can't measure its curvature from here is because of that staggering 10-meter scale. It tells us something fundamental. It tells us that even if there is an ultimate boundary out there, an edge where existence somehow wraps around on itself, that boundary is so far removed from our reality, so far beyond our physical reach, that the real frontier isn't about traveling outwards anymore. The true frontier is now theoretical. It's the space where our curiosity, our mathematics, our imagination pushes our understanding beyond the physical limits imposed by light and time, trying to grasp the nature of the whole, even the parts we can never ever directly see.